Alright folks, hello again, and in this video we're looking at the derivative as a function. So we've previously described the derivative at a point, and now we want to look at it a little bit more general. So see if we can come up with a general description where we can tell what it is at any number of points, but rather than having to do that computation over and over again for every different point. See if that makes sense. So like I said, previously we looked at the derivative at a specified value, a, and so we found f prime of a if we were given a function f. Now we're going to let a vary, and if we let it vary, we think of it as an indeterminate, it's not a specified value, and so we use x, so we don't want to trick ourselves into thinking that it's a specified value. And we basically just do the same formula. We treat the derivative of a function as a function itself. So we say f prime of x, so we let that vary, and we've got a nice function here. It looks, cosmetically, it's no different than what we had before. We just literally just changed the x's with the a's for one of our descriptions for the derivative at a point. But the emphasis here is that x is not a specified value. So the computations are very much the same type that we were making before, but we're going to find that it's easier and makes more sense to use this definition than the as x approaches a alternate definition for derivative at a point. So a little bit with terminology. Excuse me. We say that f is differentiable at a if the derivative exists there. So the new word is differentiable. And we say f is differentiable on an interval instead of at a point if f prime of x exists for all x in the interval. So it's differentiable at every point within the interval is another way of saying that. So differentiable at a point, differentiable at on an interval. Our notation, we usually use this f prime of x just like we did for at a value a, or often say at a point a. We use f prime of a. Well, thinking of it as a function, we have other notations. Oftentimes, if we've got y equals f of x, we'll look at the rate of change of y with respect to x, the derivative of y with respect to x. If we're using a function f, we'll sometimes say df dx. We might say y prime if it's clear. We might think of this more of something like an operator and think of it as kind of acting on the function. D of f or df or df of x. Your two common notations are going to be this one and that one. This one here is often called the Leibniz notation. This one, if it's at a value a, we'd write it like this: dy dx with a big vertical line to specify that it's where x equals a. Alright. So the domain of f prime of x, well, f prime of x is just a function, so it's the set of x values, the set of inputs where the function is defined. This is defined in terms of a limit, so it's a set of x values where the limit is defined. So one way of thinking about it might be, well, where is it not defined? And so the derivative is not defined where, first of all, if the function is not defined, there's no hope of that limit existing. It turns out if the function is not continuous, f prime, or the derivative is not defined there. These ones are pretty clear. We'll see with some examples in just a second. A couple other spots, a little bit harder to see, but if we think about it, it makes sense, is where a function might have, or the graph might have corners or cusps. We'll see geometrically what that interpretation is in just a second. And where the graph has a vertical tangent line. Remember, think of f prime as the slope of the tangent line, and a vertical slope is not defined. And so that would be that case there. We'll come back to that, like I said. So values where f is not defined or not continuous, these are easier to identify. Certainly something like the impression that we get here is that it looks like we've got, and this is the interpretation we're supposed to make, looks like we've got a vertical asymptote for that graph, or if you like, an infinite limit. So f not defined at x equals -2, it looks like, and it's not continuous at x equals 3. Wait, did not want to do that. Hit the wrong button. So let's say not defined at x equals -2, not continuous, take 2 here, not continuous at x equals 3. So it doesn't specify whether we've got, this or a reverse situation, or maybe they're both open, and then in fact it's not defined, but I'm assuming that it is defined. Certainly not continuous though. So f is not differentiable, the derivative does not exist at x equals -2 and x equals 3. For corners and cusps and things like that, a little bit trickier to see. But we've got two examples here. We can look at the absolute value function, and we can look at this power function with x to the 2/3 power. We've got the graph story right here. This is y equals absolute value of x. Just so we're clear, y equals x to the 2/3. And in both cases, we've got a problem at 0. Now this is continuous everywhere. It's defined everywhere. So no problems there, but we've got a corner here. And we've got what we call a cusp here. It's like a curved corner or something, you might think. And if you think about it geometrically, or think about our interpretation of the derivative, we're looking at slope of the tangent line, slope of the tangent line. Well, along this linear part, the tangent line is just that line there, continued. And same thing out here. So as we approach from the left, it looks like we've got a derivative value of something like -1. It looks like slope is -1. And from the right, it would be +1. And so that limit doesn't exist at 0. It's not the same from both sides. Or if you like trying to imagine what's happening at 0, there's no well-defined tangent line. Out here, there's definitely a tangent line. It's the line itself, that part of the line. But out here, there's no well-defined. Is it here? Is it here? Is it here? What does it mean to be tangent there? Doesn't quite make sense. It's the same sort of thing here, except as we come in, it looks like the tangent line slope is changing. And as we get right up to here, it looks like it's getting closer and closer to negative infinity. From this side, moving back, we've got slope there, slope there, slope there, closer and closer to positive infinity slope. But it doesn't exist as a number, and it's not the same from both sides. So in both cases, we've got problems at 0. This is what we mean by a corner. There's kind of a common example, and that's what we have in mind for something like a cusp. For something like a vertical tangent, you could look at this function as a nice example. Here's the graph. Once we have formulas for these, we'll revisit them and we'll see, kind of analytically why it doesn't work. Now we're just focused on the graph part. At 0, it looks like that tangent line would be perfectly vertical, and it is. But that slope is undefined. And that's what we're saying here with geometric interpretation. It's a vertical tangent line. So again, we have a problem there. Those are where the derivative won't exist. The function is perfectly fine, continuous everywhere, everything's good, but the derivative doesn't exist there. Important fact to keep in mind, if a function is differentiable at A, then it's continuous at A. We're not going to prove that, we'll just believe it. But this is not a two-way street here. The converse is not true. So if it's continuous, it doesn't mean that it's differentiable. Our 3 previous examples all showed that. This one in particular, but all 3 of them showed that. So you got to be careful. Just because it's continuous doesn't mean it's automatically differentiable. A couple things to note quick as we get kind of closer to wrapping this up. The zeros of f prime correspond to the horizontal tangents to the graph of y equals f of x. A positive tangent slope means that corresponds to f increasing. A negative tangent slope corresponds to f decreasing. When we look at this crazy graph here, what we've got in blue is the function. What we've got in something like orange is the derivative. And if you look, for example, where is the blue increasing? It looks like it's from about here up to here. Looking at the blue curve, where is it increasing again? Looks like maybe 0 out to about here. Where does it start to increase again? Out here. And if you notice, that's exactly where the gold or the orange part is positive. So that's that connection there. And where the tangent line for the blue curve, where it would be pointing down, maybe from here down to here, that's exactly where this is negative, where the derivative function is negative. So we'll talk a lot more about that, but it's kind of a first glance, just looking at the graphs for comparison. So a lot to think about there. Last thing to mention is with higher order derivatives. If we had f prime is itself a function. That's what we've been talking about, at least to find where it exists, or it's to find where that limit exists. So you can repeat this process. You can, in theory, do it over and over and over again. If you did it one more time, the result would be what we call the second derivative of f of x, which would be the derivative of the derivative. Our notation, here you see derivative of the derivative, we just do 2 primes there, so we say f double prime or you use, here would be the Leibniz notation oftentimes. Here we do that. We often use this one actually. So basically what we're doing is we're kind of applying this process twice. Applying a differentiation with respect to x 2 times. So that's where those exponents are coming from. Sometimes that's confusing for folks getting started. But basically we're just repeating our process multiple times as necessary. So here's an example. A nice quadratic function there. If we wanted to figure out the derivative, here's the difference quotient. We could do our algebra cleaning up quickly. I'll let you maybe pause the video if you like and look through that a little bit closer. It cleans up like this. The derivative then would be the limit of that as h goes to 0. You've got the substitution property here. You can do a direct evaluation, and in the end you get 2x. Well, to find the second derivative, I would just do that same process, but use f prime in place here. So I've got f prime there, f prime there. F prime is 2x, so I'd have 2x plus h minus 2x. Go through all your business there, look at the limit as h goes to 0, and so the limit of that is just 2. So f double prime is the constant function 2. And so if we look at it here, we've got y equals x squared minus 4. We've got our derivative here, which is y equals 2x. And we've got our second derivative, y equals 2. Remember that is f double prime. This is f prime. And this is just f. We'll talk about those relationships between those and what you can see from the graph a little bit more down the road, but I'm just trying to get the hang of it now with the intro. So to close, with higher order derivatives, we could continue on. We could do the third derivative, fourth derivative, and so on. Notation-wise, it starts to get a little bit messy if you're going to use the prime notation over and over again. So like the fourth derivative, I wouldn't do f1, 2, 3, 4 primes. I'll just do this parenthetical around the order of the derivative. So we won't get too far past the second derivative, but that's how we would proceed.